My name is Emily Monclus, and I'm presenting for the ROW program. I am a rising 10th grader. I'm going to go to Russian Radio Senior High School this year. I like softball and music, as well as science and math. The ROW program is a program that stands for RIT, Opportunity in Astrophysics Research. I was introduced to it through STEP, which is a science program. It teaches coding and astronomy, and I have some experience with research and astronomy through school, but I've never programmed before. So we're going to be studying neutron star mergers. In order to do that, we need to learn about neutron stars. They are stars that happen when massive stars run out of fuel and collapse in a supernova. So these supernovas can collapse into a black hole or a neutron star. Protons and electrons in the supernova will combine into neutrons, and that's why the neutron stars are made entirely of neutrons. They are relatively small and dense, about the size of or length of Manhattan Island in diameter. Neutron star mergers are when neutron star binaries or two neutron stars collide into one another. This leaves a merger remnant, which is a larger neutron star. This new star spins at extremely high speeds, and this speed will counteract the gravity from its mass and make it so that it does not collapse into a black hole immediately after it is created. Particles will interact with the magnetic fields and end up slowing it down. And at that point, it will create a black hole. Ejecta are particles and atoms that are thrown out of the merger remnant after the merger happens. These are very hot and energetic, and that creates light. There are a few parameters to ejecta, but we focus on mass and velocity here. Dynamical ejecta is one type of an ejecta. It is made from, one way it's made is from the collision of the stars, the two neutron stars, and basically the neutron stars will hit each other, and because of that, there will be matter thrown out. Another way is when the neutron stars are colliding, the outer most edges of each star farthest apart from each other will be ripped apart from the main portions, and that will also create some of the dynamical ejecta. This is partly dependent, the amount of dynamical ejecta is partly dependent on the mass of the original neutron stars, as if the neutron stars are bigger, there will be more dynamical ejecta to be made. There are nuclear reactions which synthesize elements in the dynamical ejecta, and these elements will be heavier than what is made in other events, such as gold or platinum. Wind ejecta is another type of ejecta, and the disk around the merger remnant will eject particles vertically. They are mostly dependent on the disk. The wind ejecta is dependent on the disk because the more mass or matter the disk has, the more it will eject. There are also nuclear reactions which create heavy elements, but not as much as dynamical ejecta would. When studying mergers, code is used. So I use Code Academy to learn about Python, which is a coding language, and in Collaboratory, which is a website used to create code, I made graphs for the studying of mergers. This would help me organize information and input different types of data into a code to make more graphs. Light curves are a type of graph that show brightness over time. One way that they're created is with telescopes and using telescope data. What we did was make models with code that were used to study mergers. So light is emitted by mergers because of their nuclear reactions. And light curves show wavelengths. Well, this light curves show different types of wavelengths, which is just a different light. And they tell us about the merger. Mergers will create light from the nuclear reactions in their ejecta. The more mass these ejecta has, the more light that we'll typically see from them. You can think about it as like a candle, where if you have a bigger candle, it'll make more light. Now, if you have more wicks on a candle, it will burn faster or for not as long, but it will still have even more light. So that relates to the velocity of ejecta, because if ejecta is faster, there will be more light, but not for as a long period of time. A question that we can answer using light curves is which ejecta type has a bigger effect on a light curve. These graphs show specifically blue light, kind of like in a rainbow, and how dynamical ejecta changes the light curve at slow and fast speeds at its highest and lower limits. The red lines in each graph will show the lowest limits of dynamical ejecta, and then the blue lines will show the highest. And in these graphs, you can see there's not much of a change at any point, at either speed, for the dynamical ejecta, showing that it does not make a large difference at either limit. This shows wind ejecta over dynamical ejecta. These graphs show a higher difference as the amount of wind ejecta increases. And finally, these graphs show both ejecta masses at their lowest and highest points at different speeds. Here's a comparison of all the graphs at their slowest speeds. The leftmost one being the dynamical ejecta mass graph, the middle one being the wind ejecta, and then the right one being both ejectas shown at once. These graphs show that dynamical ejecta has little effect on the light curve, because when looking at the final graph to the right, there's not much of a change when comparing it to the wind mass graph. This is helpful to know because when we're looking at other types of graphs, we can see what type of effect each ejecta type will have on the light curves. And comparing data in this way can help us make conclusions about mergers. Black holes are another merger remnant from the neutron star mergers. And small ejecta masses can mean black holes were created faster. So this means that if we looked at data and see a small amount of either ejecta, then it was likely a black hole was created faster, as there was not as much time after the merger for ejecta to be expelled. The amount of ejecta being thrown out is slightly dependent on the orbit of the original neutron stars, as if there is a more circular orbit, there's not as much ejecta thrown out. And if there is a more eccentric orbit, the neutron stars will hit each other in such a way that more ejecta will be thrown out. And that's another example of why ejecta masses would be different. In the future, we could use merger light curves to compare events. This would be helpful to distinguish events by looking at their light curves and identifying each event to create better models for each event. Another use for comparing light curves for different events, such as like supernovas, would be finding similarities at comparable points. This would be in the most active or explosive states, or like more dormant parts of these events. Overall, we learned about the physics of mergers and their light curves and what happens during mergers. We used code to analyze data, and we worked up to realism, such as using this code to create models, but also we could use it to look at different types of work in events. We use different types of light curves to look at different things. The light curve you see here would show what different wavelengths would look like over a period of time, while some of the earlier light curves would show the difference in ejecta types and what effect they have on light curves. This is all important to use data differently in the future, so we can use light curves in a different way to study different mergers or events. That's all I have. Thank you.